Okay, so in the earlier lecture we talked about this concept of mean lift coefficient and how important it is actually. Okay. So, this sort of tries to correlate rotor blade angle of attack with fixed wing type angle of attack. So, for fixed wing aerial vehicles, I mean we do not have any rotation involved, your wings are straight fixed and there is only linear translation happening. So, therefore, I mean every point on the blade or rather wing in that case, okay, every point on the wing actually has same angle of attack, same speed, same everything. But for rotary wing systems, I mean because there is a rotation so there is rotation happening. So, what happens that I mean every point on the rotor has a different speed, different Mach number and different angle of attack. Okay. So, it is more tricky to understand I mean what is the overall operating state of the rotor. So, it may happen that some part of the blade may stall, some part of the blade may not stall, and it happens actually okay, when we go in forward flight and even when we have dynamic stall phenomena called dynamic stall, which we had talked about in the very early introductory class. There also I mean we do not see dynamic stall happening everywhere. Okay. It will happen on the some particular azimuthal location and some particular radial station. So, to get a sense of at least static stall, we define this mean lift coefficient. So, it is a sort of an average value and it can be used to get an average value of angle of attack also. So, it gives you a fair idea about I mean what is the operating state of the rotor, can I extract more lift from that or it is getting close to stall. So, it is more critical for variable pitch systems. For fixed pitch systems, I mean its utility is purely from the point of view of deciding your geometry. Yeah. So, what kind of root pitch angle I will set, what kind of CT over sigma I want to extract from the rotor, because CT over sigma will remain constant irrespective of whatever RPM you operate at. So, it gives you a fair idea that okay, where I am operating at, right. So, that is the whole idea about this mean lift coefficient. Now, we will talk about one final topic related to BEMT, which is the tip loss factor. So, tip loss factor. Okay. So, if I look at the thrust distribution, so which means distribution of thrust with radial station dt versus r. Okay. So, from the ideal theory like momentum theory, this variation would go somewhat like this, okay, almost linear. So, some kind of triangular distribution would be there, very linear. So, this is from the ideal theory. Okay. While the actual variation could be quite different. Okay. So, actual variation which I am showing with red would have the lift coming down to 0 at the blade tip. Why? Tip vortex. Okay. So, because of the presence of the tip vortex. Okay. So, if I take another look at this, okay. So, this region this is sort of my tip loss. So, what it is trying to convey is that due to the presence of the tip vortex and also because beyond the blade tip there is no lifting surface. Okay. So, which means I mean any lift beyond that is 0. So, you cannot have a jump that I mean my lift is some finite value and suddenly it disappears, right. It has to come down to gradually or steeply or sharply, it has to come down to 0. So, at the tip exact at the tip, which is your small r equal to 1.0, your lift or thrust has to come down to 0, and therefore, there is a region where I mean you have a deficit of lift or thrust. So, there is a loss of thrust which we call as tip loss. So, you see this I mean in the ideal theory you still have lift in this area, right here, but in real theory there is less lift and that lift diminishes to 0 also. So, as a consequence that actually is like a tip loss. So, we can call this tip loss or consider this tip loss. So, tip loss can be viewed as a loss of thrust producing capability of rotor, and the reason for this is tip vortex. So, how does this actually looks like? So, we can and this tip vortex is there because I have a so approximately like that. Okay. So, this is my thrust distribution, and because it has to come down to 0, and of course, the way we have tip vortex in fixed wing, same way we have tip vortex in rotary wing, which is because of the difference between your top and bottom pressures. Okay. So, that you will remember, right, that the pressure over the top surface of the airfoil and the bottom surface of the airfoil is not equal, and therefore, the flow would go from high pressure to low pressure. Okay. So, which creates this vertical kind of thing which results in tip vortex. Okay. And this tip vortex can be further sort of visualized in form of the velocity field. So, if I look at this same kind of diagram, so this is the axis of rotation, this is my thrust distribution, and when it comes to 0, you have these so you would end up with a tip vortex here, and one can look at the tangential velocity across the vortex. So, you will have vorticity contours like this, okay, which is basically denoting the flow field, and if you go into the core of the vortex and look at how the velocity field varies there as a function of radius and azimuth. Okay. So, this is V theta versus R. Yeah, so it behaves like this basically. Okay. So, that is how the, so this is the velocity field as a function of your radius. Okay. So, if you go from the core of the vortex, the speed will be 0, as you go outwards it will build up and then again come down. Okay. So, you are going radially outwards from the core of the vortex. So, this is just to give you an indication of, I mean, how if you go inside a tip vortex, what kind of flow field you will experience there.
That happens at the 75% of the.
No, so this actually has nothing to do with the radius of the rotor. Actually, this is yeah.
Not the velocity. Thrust distribution. The tip happens on the 75%.
Not necessarily. No, it's not like that. Okay. It will depend on the twist and many other factors actually. Okay. Sometimes what happens that, I mean, larger rotors, they don't even have a single airfoil. So, they have two different airfoils also. So, the reason being that, I mean, for helicopter rotors, my bulk of thrust generation happens in the outboard section, ranging from say here to here. Okay. So, between say 65% to say 85%, that is the region where you will have the most thrust generation, because the moment you go to near tip, your tip vortex will influence. If you go close to the root, your velocities are less, your tangential velocity is less, because omega into r, your r part is small, or y omega y is small. So, if y is small, I mean, I do not have enough speed to generate enough lift. So, the idea is that, I mean, I will try to maximize my lift generation in this middle region and minimize my drag penalty in the outboard and the inboard sections. So, many helicopter rotor blades, especially for example, Black Hawk, if you look at the Black Hawk US60A, I do not know about the current generations, but the original Black Hawk rotor blade, its design actually had the middle section was actually a thicker airfoil, and outboard and inboard was a thinner airfoil. So, you have a one high lift airfoil sandwiched between two relatively low drag airfoils. So, low drag airfoils basically, you know that, I mean, I will not get much lift, but I want to minimize my drag, okay, or they are more conducive for transonic kind of conditions, okay, or going close to 0.8 Mach number or so on in the forward flight. So, it actually has that kind of design. So, they have SC1095 and SC1094 R8 or something. Yeah, so, there are two different airfoils. The middle airfoil is slightly thicker one and the outer airfoil is slightly thinner one, which will have less drag. So, because of all that, I mean, my thrust distribution would not necessarily say that, I mean, I have a peak at 75%. No such constraint is there. Yeah. Okay. So, this is just to give you the overview of things like what physically it actually is. Now, you can understand that what is the role of tip vortex. What was it doing for the fixed wing? Yeah, so, it was inducing some amount of some flow, okay, which was decreasing the angle of attack. So, you have an induced angle of attack, and because of this induced angle of attack, your actual angle of attack decreases. Okay. So, something similar will happen here. If I go back and look at my blade element, okay, so I look at my airfoil, which is for any particular blade element, we have ut, and then I have up, and based on that, I mean, I have a resultant flow in this direction, right. Okay, so, this becomes my u. So, you can see that up would increase, right, because of the tip vortex. See, anyhow there is induced velocity everywhere on the blade, but because of the tip vortex, this up would increase significantly, and it increases so much that it actually brings the angle of attack down to almost 0, and that is why your lift actually drops to 0 right at the tip. So, it will increase up, and therefore, my this angle phi would also increase. So, my alpha was theta minus phi. So, if my phi increases, my alpha decreases. So, the tip vortex tries to reduce the thrust or the lift at the blade tip. So, we can say tip vortex phi is your up by ut angle, right. It is the induced inflow angle, and this angle is my alpha. This total is my blade pitch angle theta. Okay. So, airfoil is at angle theta, the angle of attack is alpha, and alpha is theta minus phi. So, if phi increases, alpha decreases. Tip vortex increases up, causing alpha to decrease, and this makes lift to go to 0. Okay. Now, the question is how do I model this? There are two approaches, but we will only look at one approach which is more effective. So, there is I will just give you the name of this. I mean, if ever you need it, I mean you can go back and look at the reference. So, one approach is called effective radius approach. So, in this idea is that I mean to account for this lost lift, we sort of say that my rotor radius is scaled down by a factor, okay, because I do not have, see my thrust is coming down here. So, I will say okay, my radius is only so much. So, that I mean for a rotor with no tip loss, I only take lift up to the point which gives me meaningful answer to that of a real rotor system. So, it is called effective radius approach. So, for same CT, we scale radius down. Okay. So, that is one approach. We will not really go into that because it is less practical and less preferred approach to model. The second approach is that by Prandtl, it is called as Prandtl's tip loss function. So, Prandtl's or Prandtl tip loss function and this actually is a fairly clever way of empirically or semi empirically modeling the effect of tip vortex, because this sort of scales your inflow in a way that it changes only near the root, sorry, only near the tip. So, it actually scales your inflow, increases it by some amount by a scaling factor for that matter, and near the tip. So, your inflow will increase and your angle of attack will come down, and you will be able to mimic the exact behavior that you see in the real thrust distribution. Okay. So, let us see how it actually works, and you will also get to implement this in your homework assignment. So, we will go back to our BEMT inflow formula, because this we are going to add into the BEMT only. So, BEMT plus this Prandtl tip loss function plus lookup table, airfoil lookup table means CL versus alpha table and CDL alpha table. If you incorporate that in your BEMT, then that tool becomes very, very powerful. It can be used to design and develop or analyze anything, whichever things you want. So, recalling our expression for inflow distribution from BEMT. So, we have 1 plus 32 theta r by CL alpha into sigma minus 1. Okay. So, this is my standard blade element momentum theory formula. Okay. And what happens, I mean, if I just plot it using MATLAB, I will have a graph like this. Okay. So, inflow will just, sorry, this is incorrect graph, my bad. It would go like this. Okay. So, this is lambda versus r. Okay. So, this is how this function will look like if you plot it for a given value of theta and r and so on. So, if we include tip loss factor or tip loss effect for that matter, effect in the form of tip loss factor or rather we call it as Prandtl's tip loss function, form of Prandtl Prandtl's tip loss function. So, we are going to introduce a new function called Prandtl tip loss function given by capital F and modify this expression for my inflow like this, sigma CL alpha by 16 times F and inside the square root 1 plus 32 F capital F r theta by sigma CL alpha minus 1. Okay. Same expression as before. Now, I have a F which has come down here and F which has come inside here. So, you can see this is a empirical correction right now, but this F is not really defined empirically, but it is defined. So, F is called tip loss function, Prandtl tip loss function, and it is given by two by pi cos inverse e to the power minus f. Okay. Your e is your exponential function. Now, there is a new parameter. So, pi is your pi and f is now defined as, so where small f is given as n b by 2 into 1 minus r by r sin phi. Okay. So, there is some So, there is some sense of this physics or some, I mean, this is sort of semi empirical in the sense that, I mean, there is some connection with your actual geometry and everything, because you have N b. So, N b is your number of blades, phi is your induced inflow angle. Okay. So, there is some connection to the physics, but it is just a curve fit. So, we are artificially applying a curve correction which will change my inflow near the blade tip. So, let us define all the parameters. So, this is how it is. So, I have a capital F and this capital F is defined by this parameter, which in turn is defined by small f, which has number of blades and your phi as the functions. So, in this phi is induced inflow angle, then we have N b, which is our usual number of blades, and where r is same non dimensional distance 0 to 1, non-dimensional radius. And if you go and plot this capital F as a function, okay, so this changes like this with number of blades. This is capital F. So, capital F looks like this, and the effect of capital F is to increase lambda at tip. Okay, so this is consistent with the experiments. Consistent with experiments. So, what exactly does it do to my lambda is so near the blade tip. So, this is r equal to 1. It will make it increase fairly quickly. So, this is with tip loss, and other I can draw without tip loss. Okay. For same pitch. So, now what is the effect of this on my rotor lift or thrust distribution? So, it will now make it to come down like this. Okay. More like this. Okay. As opposed to what was there earlier. So, in earlier case your thrust could have just increased like this. Okay. So, this is dCt versus T. Yeah. So, this is no tip loss and the green is your with tip loss. Okay. So, you can see this actually is sort of a artificial correction to my inflow to enforce it to make it look like the way you observe in experiments. So, you are trying to copy or mimic experiments, and but this works very well. It is again a model, but it works quite well and it gives you reasonable estimate about your thrust, power, everything, which agrees fairly well with your experimental results there. So, now I will just quickly tell you how to implement this in code, because your job will be to implement this BEMT in the next homework assignment, which I will upload today or send you today, and that basic BEMT you will first implement and see how it works with numerical integration and everything. You will plot the thrust distribution and you will see the effect of twist and other things in the entire thing. And beyond that, I mean, you will at the end you will also get to implement this tip loss factor and see the effect of tip loss factor, how it actually changes your lift distribution. So, you will actually plot this dCt versus T and see it for yourself. Okay. So, let us quickly look at the approach to implement this tip loss function in BEMT. So, implementation. Tip loss factor. Okay, so our objective, remember, in BEMT is to do what? What do I want to do with BEMT code? What is the purpose of it? I mean, why are we doing any theory for that matter? More than distribution, I want to know the thrust and torque. The objective is that, I mean, somebody has given you a rotor and says, okay, you tell me how it is going to perform without, I mean, requiring any experimental tools. Or in some case, I mean, you have a requirement, somebody told you that, okay, give me a propeller or a rotor which will generate so much of thrust at so much of RPM without consuming more than this much of power. So, using this kind of tool, you can actually go and design this propeller for yourself. Okay. So, depending on your custom requirement, because you are building a UAV, you are designing a UAV and I have to design a propeller. So, I can design a propeller using this kind of tool, as it allows me to select multiple airfoils, I can select different geometries, I can decide what disk loading I want. Okay. So, based on that I can set the radius, I can even putter with radius and basically optimize my design to meet certain requirement. Okay. So that my thrust requirement, my torque requirements are met, and objective is to bring the torque or power down to as low as possible, while ensuring that I have a basic performance for thrust. So that is the idea. So that is why, I mean, I want to write a code like this, because for example, the other day I had a meeting with VSSC and now they are saying, okay, you do the entire project for Martian helicopter. So, starting from scratch, I mean, all they are going to tell me is that, I mean, go and design a Martian helicopter which will maybe fly for 2 minutes while carrying a useful payload, some experimental payload on Mars, and it will fly for maybe say carry a camera. Okay. Because current Ingenuity helicopter, when it was flying, it had just a small tiny camera and nothing, no other payload. But here, I mean, now if ISRO wants to do some experiments, they would put some maybe a payload which will try to profile the Martian atmosphere. So, goal could be that, I mean, okay, I will fly a little bit up and down and measure temperature, pressure, whatever, I mean, okay, across whatever heights I can fly to, and also maybe use it to map the environment or whatever. So, they may put some 1 kilogram payload, let us say. So, now if you are carrying a 1 kilogram payload and you have to fly for 2 minutes in that kind of rarefied atmosphere, where do I start? Right. So, I have to do a conceptual design study, and the crux or the starting point of conceptual design study is the performance calculation. So, in this current course, we are not talking about design, we are only understanding the mechanics which is used for design. So, in the next semester course, when you take up the autonomous unmanned aerial systems course, that course will actually train you about design. So, use whatever we have done in this course, apply all that knowledge and develop a code which will allow you to do conceptual design studies. And these tools are very powerful. I mean, I already gave you example that with these tools, I mean, we are able to design all our UAVs with 5% accuracy. An engineer is super happy if he gets 5% accuracy with his tools, because we are not mathematicians. We are not going to say, I mean, I want 100%, 99.99% accuracy. No, that will never be achieved, but 5% accuracy is fantastic. I mean, whatever I am designing, I am actually able to get same thing, mostly better than that when I actually build it in the real world. So, this tool which we are going to develop now would go as an input in the next semester's work. So, this BEMT tool then becomes very important and powerful. So, design or even otherwise, I mean, if somebody gives you a UAV and says, okay, I mean, I want to know how it is going to perform, somebody is claiming such and such things, but I do not have a capability to go and experimentally verify everything, can you just quickly check things out? So, a lot of times people make claims that, oh, my drone will fly for 5 hours with battery power, whatever, I mean, n number of hours or whatever time, and they are showing geometry which does not look realistic. So, using a tool like this, I mean, I can easily go back and verify such things. See, the simplest thing is I can do momentum theory and figure of merit business, but if I want something more rigorous, then I can use a tool like BEMT. So, in this now we will try to implement this T plus factor to make it more realistic. So, that so any tool you develop, the first and foremost thing is to verify whether the tool is correct or not. How do you verify? With experimental results, right. So, I will give you some experimental results, I will say, okay, now write your code and match with this. It will not match 100%, but it should come within 95% at least, right. So, that is the idea, and that accuracy will improve if I use T plus factor. Okay, so to get the performance, so my objective is to get the CT integral, okay, and CQ integral, right. Okay. So, do I have those? Yeah, CT formula. So, CT is half, maybe I will write it more clearly, half 0 to 1 sigma CL alpha into alpha. Well, let us write down alpha also as theta r square minus lambda r dr. Okay. CQ is half sigma CL alpha into lambda into theta r square minus lambda r dr plus half sigma 0 to 1 sigma C D naught r cubed dr. Okay. So, in BEMT my objective is to evaluate these two integrals, okay, and in that process I require lambda. So, I go back to my lambda, which is given as sigma CL alpha by 16 f into 1 plus 32 f theta r by sigma CL alpha minus 1. Okay. So, I need to evaluate the CTCQ using this lambda, but then I do not know f to begin with, right. So, how do I start? So, before we begin we calculate lambda with f equals to 1, okay, which is fine. I put f equal to 1 everywhere. Note that this capital F is also function of small r, right. So, it is not just a static parameter or sorry a constant parameter, it is actually a. So, this lambda will now become a vector, your CT DCT is a vector, DCQ is a vector. So, once you integrate everything it will become 1 point, CT and CQ have 1 values, but the distributions are vectors, because we will do this evaluations at multiple points on the blade from 0 to 1. I will say if I use your normal rectangular rule, very easy thing, okay, I will put 200 points. Okay. So, I will give you a choice between using rectangular method, or I will teach you the Gaussian quadrature. If you want to use that, you can choose either of them, they are both fairly trivial and straightforward, not so complicated. But yeah, so either way, whichever way you do, I mean I will get a distribution and that I have to plot to see the distribution of CT versus R, CQ versus R, lambda versus R. So, all those things you will have to plot. So, calculate lambda with f equal to 1. Now, what are the steps? And then use lambda to get new value of capital F. So, we have to do this in an iterative manner. So, the steps are like this. Steps, first step is solve for lambda with f equals to 1 is no tip loss. So, we set f equal to 1 in my formula for lambda r equals to sigma CL alpha by 16 f into 1 plus 32 f theta r by sigma CL alpha minus 1. Number 2, step number 2 is now calculate f using above lambda. So, how do I calculate? So, first I will calculate small f r, which is given by n b by 2 into 1 minus r by r sin phi, or I can simplify it and then write it like 1 minus r by lambda r, because lambda is small only. So, I can keep it like this. Okay. So, I can 1 minus r by lambda r, and then use this to calculate my capital F as a function of r, which is 2 by pi cos inverse exponential to the power minus f. Okay. So, we have formula 1, formula 2, formula 3. Okay. Yeah, so the sin phi is phi is lambda by r. So, that is why I said, I mean, you can write it like this also. If you want, you can use the sin one also, that is not a problem. I mean, only thing is you cannot then multiply with r. Yeah. So, phi will then be lambda by r. Yeah, right. So, because my inflow angle will be very small, so I can always approximate sin phi with that, and I can write it like that. So, now once I have calculated this capital F, which is now new value of capital F, I will reuse this. So, recalculate lambda using F from step 2. Number 4, recompute F using 2 and 3. Again recompute lambda, and this step 4 and 5 is basically I have to iterate till lambda converges or capital F converges, right. So, you have to basically compare between successive steps of lambda or this F to get this convergence part checked. Okay.
So, why are we still going to write F in the equations? Like we can replace 1 instead of
I mean, I can write it as a function. So, it becomes my lambda function. So, I do not have to keep typing lambda again and again, right. So, it is a more clever way of coding, where my function is directly giving me lambda. In MATLAB, I mean, I can define lambda as a function and it takes f as a parameter. So, independent of whether I am using f as 1 or f as something else, it will always give me lambda, just to do it cleverly. Yeah. But bottom line is that this is my formula I am using. So, I do not want to change my formula to avoid creating confusion. So, I say initially my f is 1 because I do not know f. Yeah. Like any iterative process, you have to start with some guess. So, this lambda with f equal to 1 is a guess. So, I keep calculating this back and back again till I see that my f or lambda stops changing. So, between every 2 steps I will find out a difference norm and make it go to 10 power minus 6 or something. So, it is small enough. So, that I know that okay, I mean between 2 steps my lambda is no longer changing or my capital F is no longer changing. Once I have reached that, then I say okay, yes, it is converged, and note that I will do this computation for entire 0 to 1 in one shot. So, you are not doing it for one point at a time, because in MATLAB I can write a loop for I mean going from 1 to 200 points or whatever, whichever way, or even you can, if you are clever, you can use the MATLAB's dot notation to directly multiply arrays continuously. So, you can do a direct array multiplication, square root, everything, but you have to do it carefully, otherwise you will make a mistake in that. So, anyway, whichever way you do it, I mean does not matter, but finally we have to do this. I start with f equal to 1, compute lambda, use lambda to get f again, keep repeating it back and forth till I see that my f no longer changes, then I am done. So, with that I have now gotten a converge value of lambda, which I will put back into CT and CQ rather to get my thrust and torque and everything else. So, that is my final result, and I can see the effect of this. So, I can also save my lambda without f, okay, or with f equal to 1 to compare that how that lambda look like and how my current lambda would look like. I can even plot my angle of attack, right. So, my angle of attack is my alpha is theta minus lambda by r, right. So, I can plot my alpha also and see how it is varying actually for a given value of theta. Note theta would also change now. I can give you a twisted rotor, linear twisted rotor, or I can give you a hyperbolic twisted rotor. So, in your assignment you will get to check all those things. What does my hyperbolic twist do? What does my say taper do? Hyperbolic taper do? I think I have not given you taper problem, but I will probably give you the twist problem. So, look at the different effects of twist and see how it affects my inflow distribution. So, I will plot lambda, and if I make twist, you will see my lambda will start becoming uniform. When I do not use twist, you will see the lambda will be more non-uniform. But finally, for all cases your thrust will also always come down to 0 with the tip loss factor. Without tip loss factor, you will see it is going straight. So, all these things you will be able to check for yourself. So, it is just for you to understand this concept in a more physical manner. See, no code can help you solve problems, they are only tools. It is people who solve problems by thinking in a clear manner. So, you always have to get to the bottom of the problem. If something is happening, what is causing that? Always ask this question. If you ask that question, you will be able to understand things better. You have to keep asking this question till you get the answer to that question, that why this is happening. Not that, okay, in the typical Indian way of doing things, chalta hai, right, I do not care, right. So, you cannot do that. I mean, if you do that, then I mean you are ignorant person, okay? You will not learn what is causing it, and once you understand what is causing it, you will know better ways to solve the problem. Okay? So, when people try to, so this is like, I mean, modern medicine does not cure your disease, it simply cures the symptom. As an engineer, will not work like that, okay? Will not cure the symptom. This is, I see this, okay, there is some problem happening, I will put a tape on that, okay. No, that does not work, okay. I have to understand what is causing this problem. If I see vibration, I have to understand what is causing this vibration. Vibration has to come from some excitation. So, there has to be some unbalanced force. Where this unbalanced force is coming from? What is the source of that? Okay. So, all those things, I mean, you should be able to relate. Okay. So, everything finally comes down to very simple, very simple physics. So, that is why simple physics understanding is the most important understanding, okay. Rather than, I mean, understanding very complex tools. Complex tools would never allow you to understand fundamentals. The problem with complex or sophisticated tools, so I use this terminology called garbage in, garbage out. Okay. Have you come across this? GIGO? No? Yes. So, this term basically implies that, I mean, you take a very sophisticated code, I mean, there are so many tools, ANSYS, Fluent, Nastran, Patran, whatever. Okay. They are very developed, well developed, nice tools, fairly accurate. But the problem is that you use that tool, you make a mistake in input, the tool will happily give you an answer without telling you that you have made a mistake. Okay. There is no way for it to check it that you are, because I mean, the tool thinks, I mean, you know what you are doing. So, whatever you have done, it takes it as a right thing. So, now your input is wrong. So, your output may be an answer, it would be an answer, it will not necessarily break down, it will always give you an answer, and that answer may be completely wrong. So, now if you base your judgment based on that, you are going to be in serious trouble, right. So, that is why these fundamental things are very important. Everything you do, even if you use a very complex and sophisticated tool, you have to have a means of checking that you are doing it right. You should be able to check it from very basic mechanics. So, if I want to look at a bending problem of some aircraft structure, that okay, if I apply so much load, my wing will bend so much, right. Other day I was talking about, I mean, this UAV which is bending like this, right. So, I mean, maybe the guy who was analyzing, I mean, he did not apply the boundary conditions correctly, but or he did not have the correct estimate of the strength of the structure, right. So, modeling the strength of the structure in the correct manner would be very important. I am just giving you examples. So, sometimes, I mean, if you use complex tools, you may make a mistake. Therefore, doing it with the simple, very basic validations, basic checks would always give you the correct answer, to give you confidence that I can use a complex tool for this. Okay. So, that is why I mean the Gordon Lischman, who is a legendary helicopter I mean engineer, his book is our reference textbook. He taught me helicopter aerodynamics. His favorite go to theory was momentum theory. Okay, so, he has published so many papers on momentum theory, you cannot imagine. You will think momentum theory is such an old thing, who is going to work on that, right. And he has so many good papers actually using momentum theory, where he explains so many things using momentum theory. So, that is what that is the power of simple theory. Okay, so I hope this is clear, okay, how to implement this part, right. Any questions on this?
Talk that you have taken here is a sum of quotient on thrust. What is the second element in that, sir?
No, so this is the two parts. I mean, my torque expression from earlier, I just copied the same thing. So, it has induced power part and the profile power part. So, this is profile and this is induced. Yeah, so this is lift into lambda, right. So, lambda dct is my induced power and then integral of your drag is your profile power. It is the same expression as before, it is nothing new. And yeah, one more important thing is that normally when I use BEMT for analyzing a hovering helicopter or a UAV for that matter, then I have to make sure that especially for helicopters where my pitch is changing, I have to adjust my pitch to match my CW. Okay. So, one way is I mean I can give you okay, solve the problem for this value of theta. In other case I can say okay, I have a hovering rotor. So, you have to then find out the theta which will give me the hover thrust also. Okay. So, remember that. So, in the beginning remember we got value of theta in terms of Ct by 6 CL alpha something we got, right, using blade element theory and momentum theory. And we got two expressions, one without twist and one with twist. So, that can become my starting point. I can use that theta to get particular value of Ct. That Ct would not match your desired Ct, then I may have to adjust theta. So, that is your trimming problem. Means I mean when the pilot is trying to fly, he has to adjust the collective to take it to a point where he is hovering, right. So, because now I am including the tip loss factor, I would require slightly higher value of collective than the simple theory formula to get the same CW or same CT. So, that is just a comment, probably not relevant for your homework, but keep in mind. Okay. So, yeah, so this Gaussian quadrature thing, okay, this may be slightly complex for some of you. So, if all of you are comfortable with the rectangular integration, okay, so fine. So, I will send you some handout on this Gaussian quadrature, okay, to give you a clarity, and if required we can discuss in next class a little bit, okay, on that. Okay. So,
the printing like the plots in printing gets like very blurry and it's not even like recognized.
no, so then you don't know how to plot.
No, the plot comes very nicely in the
No, but the problem is, see, you are using from MATLAB, it will look very good actually, okay, but you have to make lines thicker and you have to use different line types to, if you are putting multiple lines, you have to use different line types. So, when you put it on the Word document, okay, the lines should be distinct, do not use color, always use black. Okay. If you use color, it will come faded in black and white printers. Yeah. So, I mean what you are saying is very silly, okay. I mean you are not printing it right basically. Okay. So, always make your graphs black and white, okay, and always this use different line types like dash, dot. See, in MATLAB also if you click on the graph, it allows you to increase or decrease the thickness. Okay. So, do all that and then put very big font sizes, do not put 12 point, 10 point, because when you put it on the thing it will become tiny, not readable. Okay. So, those things you have to learn and fix it. Even when you put in PowerPoint, most students make mistake, their graphs will have font size which will be microscopic. So, that actually is a really bad thing if you are making a presentation with that, because people will try to read that and break their eyes and they will not be able to read. So, it is a very big turn off. So, always put nice clear diagrams, okay, which are easy to read, font size are big enough. So, that same thing applies for printing also. So, if you put it properly, it will come out nice. Okay. The reason I force you for hard copy is that I mean grading on computer is painful. Okay. So, but fine, I mean in this case programming code. So, if you have difficulty you can submit the last assignment in PDF. Yeah. Yeah. It also spams my mailbox. So, maybe I will have to create a then assignment on the this hello IITK. So, you can upload it there, because otherwise I mean I get 15-16 emails all of a sudden. Okay. So, this is not directly related to our theory, but nevertheless it is a very powerful integration tool to do all kinds of numerical integration, and almost all helicopter codes out there or BEMT codes out there, they all use this Gaussian quadrature. So, from wherever you take. So, this is about numerical integration using Gaussian quadrature. Okay. So, this deals with your definite integrals of this form, and the whatever formula I am going to give you, this can actually rigorously be derived also, but we will not bother about that. So, this is my integration I want to solve, minus 1 to 1 f x dx. This I can write as actually a summation from I equal to 1 to m w I f of x I. Now, note that I mean these are just normal things, they have nothing to do with any of our symbols you have used so far. So, w is a weighting function here. So, this is weight or weightage, and x I is the locations where I will do the function evaluation. So, this Gaussian quadrature tells me that I can express a definite integral of form minus 1 to 1 as a summation of 6 function evaluations, that is it. The question is, where do I do these evaluations? So, that is given. So, here we will use m equal to 6, and correspondingly I will have these values for the function evaluation points. So, f of x I means I am going to find out the value of the function at given point x1, x2, x3, x4, x5, x6. So, I will do that, I will do the function evaluations and I will multiply with these corresponding weights w1, w2, w3 to w6. So, w1 f x1 plus w2 f x2, if I just do this summation, it will give me the integration minus 1 to 1 and with a very high degree of accuracy. So, what are these points where I do these evaluations? So, x1 will correspond to minus value and x6 will correspond to plus value, hence minus plus, and you will have to type down all these decimal points in your code for accuracy. You cannot leave any of these decimal places, and we will go to fairly high decimal places. So, 0.9, 32, 4, 6, 9, 5, 1, 4. So, 932, 469, 514. Likewise, I have x2 and 5 also minus plus, this is 0.6, 612, 0938, 6, and then finally x34, that also will be minus plus. So, the first number is minus, second number is plus, note that, hence minus plus. Here it is 0.02, 3861, 9186. So, 0238, 619186. So, these are the 6 points, and similarly there are 6 weights, 1 comma 6 same weightage. So, this is 0.1, 713, 24492, 24492. So, 171, 32, 4492, it has all plus sign, because it is a weightage. W25, so 0.2 and 0.5 weightage, 0.36, 0761, 573. If you search on internet, you will find these numbers also. 6 point Gaussian quadrature, just double check in case I I make a mistake or you make a mistake and you are not getting correct answers, you can just double verify from internet. Most numerical analysis books also have these 0.4679, 139, 35. Okay. So, 6 points, 6 weights. But how does this work? The integral I have to solve is CT, which goes from 0 to 1, but this integral is from -1 to 1. What do you do? No. Who told you that this is an even function? Okay. You cannot do that 2 times. What do you do then? How do I apply this quadrature scheme to my integral from 0 to 1?
Function is not defined.
No, function is any function.
Anyway,
So, here it is my dct. Okay, so, integral of fx dx is my dct into dt. Okay. So, I mean dct itself, right. So, that is the integration it is there. Okay. So, we have to solve this integral which is 0 to 1 dct, let us say. Okay. But our formula works from -1 to 1. Nobody could find the answer.
We take interval from 0 to 1 and then calculate points and weights.
No, how?
The points and weights are
Yes, you
calculated
forgot
on-
about change of variables. Yeah, this integration thing was long ago, right? Okay. When you were studying in kindergarten. Yeah. So, who remembers 20 years back, right? 25 years back maybe for some of you. Right. So, yeah, I understand, right. But anyway, so there is something called change of variables which allows you to shift from this to that. So, it is very simple. I mean, I just have to use a new variable, let us say t, and I call this t as ax plus b. So, what happens now if I go to x equal to -1, t is say 1. So, minus a plus b. So, what I am doing is that I am changing this to a generic integral of a to b f of t dt. So, this integral I am transforming into this new integral. It will allow me that I can set any arbitrary a b and anything, okay, without changing anything else for me. So, if you see I put x equal to -1, then it becomes minus a plus b, and if I put +1 it becomes b equals to a plus b, right. You solve these two, I get capital A equals to b minus a by 2 and capital B equals to a plus b by 2. Okay. And my function t now looks like t equals to b minus a by 2 into x plus a plus b by 2, which means if I try to do a equivalence between dt and dx, right. So, my dt would be equal to b minus a by 2 into dx, right. So, with all this information I can now easily write my integral as a to b f of t dt equals to sigma of I equals to 1 to m, weight does not changes, it remains same, and now instead of f of x I do f of t I, where t I will be found using this formula, right, using same values of x. So, x i's will be same as before. So, f of t I into see dx will be replaced by dt. So, dt equal to b minus a by 2 into dx, right. So, we have into b minus a by 2. Okay, so, that is the entire correction, and here I can put t I equals to b minus a by 2 into x I plus a plus b by 2. So, now you see I have transformed my integral from -1 to 1 to any a to b. So, I can put a equal to 0 and b equal to 1, right. So, this is the process which will allow me to do, but the catch is that I will not do this integral for entire blade in one shot. which means I am not going to use 6 points, because I need to plot distributions also. So, I will break the entire blade into say 20 segments. Okay. So, equal space segments. So, 0 to I mean 0.05, 0.05 to 0.1, 0.1 to 0.15 like that. So, 20 intervals. Within each interval I will apply this integration of 6 point Gaussian quadrature, because it is a general, I can do it from any A to any B now, not a problem for me, but all this requires careful coding. So, if you feel it is intimidating for you, just go ahead with the simple rectangular rule. Yeah. So, take 200 points, 300 points, nobody cares because all the work will be done by computer. So, maybe take 300 points and then just equal space points and just find out f x and do the integration this dct and get the plots, fine. So, if you need any help on this, I mean you can talk to me, but otherwise let us see, I will upload the homework today, and again check the things right away, and if you have questions ask me by Monday, okay, no later than that. After that, I mean no extension, nothing. Any difficulty there, come to me, I will sit with you and help you solving the problem. It is very important, okay, fine. So, we will stop here now.